So, as I said, this is a hugely important chapter. And so the two, if you boil the whole thing down, these are the two most important things. Be able to find the derivative of any function. That's what we're going to start today. And we're going to learn lots of different techniques and lots of different rules that you have to learn how to do each and every individual one. Aside from that, I want you to make sure that you understand what it is. What is the derivative? What is it good for? And then along the way, we're going to learn lots of different notations. And there's a lot more, but if you go at the core, this is the most important thing. Okay. In the chapter after this, we're going to look at all different kinds of applications of this. Applications of the derivative, after we know how to do all of them. So let's take a peek at, first of all, what we've got. So I'm going to do a quick explain. I would say, let's suppose we have a function. We have a function, and I'm going to call it f of x. It's a random function. I think I'd sign you up to be my editor. Suppose we have a function f of x. It can be any kind of function that is. The derivative of f of x is called f prime of x. Okay, that's the notation, f prime of x. We've gone through it from a very broad picture many times. Who can tell me what f prime of x, the derivative, who can tell me what it does? What is it good for? Jenny? Exactly. So, put this in here. F prime of x tells the slope of the line tangent to f of x at any x value. So f prime of x tells the slope of the line tangent to f of x at any x value. Okay. All right. To the front board. Just to make sure we got that, and then we're going to find derivatives. So we've got this graph going on here, and I have the blue line, the blue curve that is traveling from negative 10 to positive 10. Okay, and the green dot is actually the slope, the actual slope of the line tangent. Okay, so if I pause this right here, well, let me move it right here. Okay, and I draw the line tangent. The blue is our f of x. The purple is the line tangent at x equals 5, or it looks close to 5. This dot right here represents about 1. See that? It's about 1. That means the slope of this line, the line tangent, is 1. This y-coordinate is the value of the derivative when x equals this 5. Now look at my scale. My scale's from 5-2, so this may not look like 1. Okay, but this, when x is 5, the value of the function is up here. The slope is equal to 1.
So you're finding you're finding the slope at that one point?
At this one point. Okay.
Okay.
Go ahead.
Uh,
Okay, make it simple. What's the slope at this point? 0. Okay? And what is where's the yellow, the green dot? It has a y value of 0. So if I go over here, see how the slope here is negative? And I said to you, hey, what is that slope? You'd say, well, whatever the y-coordinate of this one is, it's negative 0.98. The slope of the purple line is negative 0.98. Yes. Never a stupid question.
You can only have like one specific tangent line at one point. You can't have,
Exactly.
like, more than one.
Exactly. Right. And yesterday we talked about that cusp, like on the absolute value. That's one where you'd have more than one, and
Okay, and then
that's why it's not differentiable. Okay? So, as your x value goes from left to right, like if I stop, I don't know, like stop right here, okay? The slope of that purple line is negative 0.6. If I go over here, the slope of that purple line is 0.46. If I go up here, the slope of the purple line is 1.06. Now if you were to plot all of the slopes, you get that green line. That green line is the derivative of the blue line, of the blue curve. So if you have blue curve is f of x, the green one is f prime of x. It's a totally new function. It's a brand new function. And all you have to do is plug in the x value into that new function, and it tells you the slope. Okay. Am I beating this to death? Okay. All right. So let's. Oh, look at that. Okay, so if you do this a whole mess of times, you start to get good at being able to compute the derivative all by itself. Okay, so what we're going to do is we're going to start small, we're going to build up, and then we're going to end up being able to do really super complicated ones. Okay, first function, f of x is equal to 4. Okay, f of x is equal to 4. Can you picture this? Picture that in your head. What is the slope at any point on this graph? 0. Okay? So if I plug in f of x, you get f prime of x. It's always 0. Okay? It doesn't even matter the x value. Yes? Oh. Yeah. Right there. Okay. All right, next one. Okay. Y equals negative 5x. Okay, picture that line. The slope of the line tangent is actually equal to the slope of this line all the time. So, what's the slope of this line? Negative 5. So if I plug in the f of x, or the y equals, I get dy dx, which is another name for the derivative, and it's equal to negative 5 all the time. Okay? Every function has a derivative. Jot that note down. Okay? New function. Yes? I'll get to it.
Okay.
For right now, it just means a derivative.
Okay.
It's really cool why it works, but well. Okay, new function. Can you picture the function? Okay? The slope of the line tangent to this is not the same all the time, like the other ones were. So this means it's not going to be a constant function like the other one is. Okay? So let's see what it is. What is the derivative of x squared? It's the line 2x. Okay? So, what I mean by that, whatever. So what I mean by that is if f of x is equal to x squared, that means I've got some parabola that looks like this, right? And then I'm saying that its derivative is equal to 2x. That means I can pick a point, any point, and I can find the derivative, I can find the slope of that line tangent. For example, here's x equals 1, 2, 3. And I say, let's draw the slope of the line tangent when x equals 3. So that's right here. Okay? The question is, what is the slope of that line? It's 6. Because the slope of the line is equal to the derivative when x equals 3. And so it's 2 times 3, which is 6. Make sense? That's what the derivative is good for. It finds you the value of the slope for any x value. Okay? Okay, let's do another one. New function. Can you picture this in your head? Okay? I wonder what the derivative is. Click it in. 3x squared. Okay? Look at this. The derivative is a parabola. Okay? So if you want to find the slope at any given point, you just plug the x value into the derivative, and it tells you what the slope is to this function. Make sense? New function. Any guesses? Xander, what do you got? 2x plus 4. That's correct. Every function has a derivative, and the derivative is a brand new function that is derived from the original function. Yeah.
I have a question about last derivative we found.
Yep. This one?
Yeah, 3x squared. Would the derivative of the derivative be 5x?
It would be
Or 6?
6x. So you're starting to form a pattern. Okay, here's what happened. Newton did this that long way with the limits and the f of x plus delta x, like hundreds of times, until he finally said, wait a second, there's a pattern here. Then he wrote this shortcut, and the shortcut is what you learned last year in pre-calc. Okay? Read that. Okay? You do something long enough, all of a sudden you can start to see what's going on. And then you can see the bigger picture. Okay? Everybody imagine it. Okay? Okay, what is the derivative of this function? What do I hear? Let's see. See if you're right. How many people had it right? Hey, what happened to the 1? Remember this one? The 1, the part of it that's the 1 is the 0. So the derivative of a constant is 0. Yeah. It was the derivative. It was called the derivative when you learn this thing, this rule. Yeah, anybody remember what the name of that was called? You'll remember it after this. Okay, we did this one. Okay. Oh, this one's weird. There's no numbers in it. Can you picture this graph? What's the slope of this? At any given point. Okay, so it's M. All right, we're now going to summarize what we just did here. Okay, and we write our own rules here. That's how this works. Okay, we write our own rules after we figure out the patterns. So, here's what we got. So, based upon all of this, if I have, we're going to write our rules. First rule, if f of x is equal to some constant, k is some number, then what is the derivative of that? 0. Notice, I didn't come up with the rule, you guys did. Okay? Rule number 2. F of x is equal to k times x. If f of x is equal to k times x, what is f prime? K. It's the slope. Okay. I got to go to slow-mo and go past it. Okay. Remember the goals? Find the value of any function. Find the derivative of any function. And we're going to get pretty wacky functions. We just got to start here. Okay. Where should I go next with this? What should rule number 3 be? X squared. So, what if f of x is equal to x squared? What is the derivative of x squared? Two x is correct. Okay, watch this one. F of x is equal to, well, let's just do the next one. X cubed.
Right.
3x squared. Okay. Okay, this is the tricky one now. F of x is equal to k times x to the nth. This is the biggie. This is the one that's in the book. Yes. The derivative, if you follow the pattern, is you take the k, You multiply it by n, and then you multiply it by x to the n minus 1. We're using the power here, the exponent. Okay, it's the power. This is called the power rule. Okay, that was the name that it was given last year. Okay, this is the power rule. It's the first fundamental rule of finding a derivative. Oopsie. Poor guy. No room left for him. Okay? Now, if you find, these are all single terms. Okay, but watch this, it's really cool. The derivative of a sum is equal to the sum of the derivatives. So that's why we can do a new one here. If I say f of x is equal to x squared minus 3x plus 4, and I say, what is the derivative of this? The derivative is each of the individual derivatives, as long as we're just adding or subtracting them. So the derivative of x squared is 2x. The derivative of minus 3x is minus 3. And the derivative of the 4 is 0. Okay? I can put the 0 in here, but then we simplify it.
So you can do that with like to the power of like the 20, and you could just, not that we should actually do that, but
Well, I think we should. Pi times x to the 203rd power. Now, see how this is the prime? It's called the prime character. If we have a function called y, then we can write y prime. And you've seen that on the other ones. So if this is the thing here, what is the derivative? 203 times a pi, the order there doesn't matter, times x to the 202. Piece of cake. Okay? Yes? Mm-hmm. If I wanted to do the second derivative of this, which we can find the derivative of any function, which means that you can find the derivative of the derivative. And the way you do it is you say double prime. It's a prime of the prime. So the second derivative of this one would be 203 times 202 times pi times x to the 201. Yeah. Write the double prime. Yep. Because then it looks like y squared. It's the notation. Actually, we attribute. Newton was a good mathematician, but he was bad with notation. And Leibniz, remember the guy who also discovered it at the same time? He used notation that we still use today. He invented the dy dx. Okay? All right, well, we're not done yet. We're kind of far from it. So, variations of this. Okay? We'll be doing lots of problems. So that's number 6. Number 7, what if we say f of x is equal to x to the negative 4? does the rule apply? As long as it fits. What's k? 1. What's n? -4. So we can, no problem, we can apply that rule. F prime of x is equal to -4 times x to the, when in doubt, write it out. -4 minus 1. So this is -4 times x to the -5. That's what the derivative is. Make sense? Okay. So knowing that, say that again. This can be written either any way. Here's the deal on this. You need to know that this is the same as this. Okay? Because on the AP exam, they could write it either way. I don't know, like a multiple choice. Okay, new one. Oops. 3 over x to the 7th. This is going to be interesting. Okay? We'll see where you went with this. Who's got an answer? Now you're scared to answer. Megan? -21 x to the -8. Anybody else get that? Okay. Did anybody get 3 over 7 x to the 6th? Okay. That one's wrong. Here's why. It wasn't meant to make you feel bad. The people that had the same answer, they didn't raise their hands. Okay? Here's the deal. You see this 3 over x to the 7th? The whole function does not match kx to the nth. You see? Because the 3 is on the top. That's why you can't do this separately. We never set a rule that handles this as it is. Okay? So we cannot apply a rule that doesn't match it. So what you have to do is you have to rewrite this. You have to write this into a form that matches the power rule. If you don't, then you can't apply the power rule.
Are we trying to get everything into the power rule?
Right now, yeah. Everything that we can, we try to put it in that form. Then, now that you see it, see it's k times x to the nth. Bam. Now we can do it. So 3 times -7 times x to the -8. And then you always simplify. It's -21 over x to the 8th. Which we can write. We start with this, but then we can also write it like that. Yeah. No. We'll get in the habit of knowing that each of these are equivalent. At some point, I might say only positive exponents from now on. Okay? But know that you can write them both ways. All right, now I got a wacky one for you. So what would we do with this? Y is equal to 4x to the -2. Does it fit the format of the power rule? Kind of, but not exactly. See the parentheses? They mess it up. Okay? So we have to rewrite this until we can get it to look like k times x to the nth. That's the bottom line. So we got to do a little algebra here. Now, how you get there, you can go this in different directions. I'm going to do it this way. I'm going to say this is the same as 4 to the negative 2 times x to the negative 2. That's how we can apply the power to each of the individual factors. And that gives me 1 over 16 times 1 over x squared. Does this fit the format of the power rule? Not yet. I'm going to go revert back to the x to the negative 2 because I went too far. So I'm going to rewrite this as 1/16 times x to the negative 2. That now fits the power rule. K is 1/16, n is negative 2. It's only now at this moment that we can apply the power rule. So the derivative is y prime is equal to 1/16 times negative 2 times x to the negative 2 minus 1, which is negative 3. And then we clean it up. Negative 2 over 16 is negative 1 over 8. And technically this is x to the negative 3, so it's 1 over x cubed. So I would write this the best possible way. Negative 1 over 8x cubed. So for this wacky function here, if you want to know the slope of the line tangent at any given x value, you just plug your x into this function, and bam, there it is. Okay? Any questions? Okay, let's see if you got this. So, let me go over this side. So I'm going to give you a brand new one. Give you a brand new one. And see if you can do this one. It'll just be a small, quick one. Ready? F of x is equal to 5 plus 3x squared minus 4x to the 7th plus 8 over x to the 3rd. What's the derivative of that function? Okay? All right. Now you're ready to do your first homework assignment, okay? The second homework assignment, first real one on derivatives. So you can start jumping into it. I gave you like a million problems, just so you know. Okay? So, but remember, here's where we're going with this. We got to know how to do square roots. We got to know how to do like the sine and the cosine and the tangent. Okay? And those are all ones that we're going to do in this section. Normally you would go in the correct order with the highest degree first and move on your way down. Yeah. Let's see. Start working on that. What's today? Wednesday?
Yeah.
Is there 2 parts to that one? That's the next one? I'm going to say try to finish it by Friday, but I don't think we'll go over it officially until Monday. Because we're going to just do tons and tons of problems, and we're just going to be cranking out all the new rules. That's going to be the whole point of everything. All right, very good day today.